Let's now take what we've learned about intermolecular attractive forces and try it on some problems. Which one of the following nonpolar molecules has the greatest attractive force? Well, you can examine the molecules and identify that they're not polar, you can take my word for it. But when it says not polar, that means it can't have dipole-dipole attractive forces, and it can't have hydrogen bonding as an attractive force. So the only force left are the London dispersion forces. London dispersion forces vary based on the molar mass, the mass of the molecules. So let's go ahead and look at the molar mass. For nitrogen, there's 28 grams per mole. For this silicon molecule, there are 32 grams per mole, 77 for this germanium molecule, and for bromine, 160. Because London dispersion forces are directly proportional to the molar mass, bromine will have the greatest attractive force and nitrogen will have the smallest one. If you look at nitrogen, it's a gas at room temperature. Bromine is a liquid at room temperature. So you can see the behavior is reflected in its intermolecular attractive force. Which of the following has the greatest intermolecular attractive force? Again, these are nonpolar molecules, so I don't have to worry about anything but London dispersion forces. So I look at the molar mass of each of these, and I see that iodine has the greatest. The smallest one would be fluorine. Which one of these molecules has the greater attractive force? Well, these two have about the same mass, so their London dispersion force is going to be essentially the same. What is the difference? The difference is oxygen has two non-bonding pairs on it, so it's going to be polar. This is nonpolar. Remember, when it's all carbon-hydrogen, it's nonpolar. So nonpolar, polar, this has dipole-dipole forces on top of the London dispersion forces. So the this is called dimethyl ether, and that's called propane. The dimethyl ether has a greater attractive force. Which is the polar molecule? Well, if I look, this has oxygen in it. This does not. So the polar molecule is ethylene glycol. So which molecule would have the higher intermolecular attractive force? Of course, ethylene glycol, because not only does it have London dispersion forces, but it has dipole-dipole forces. Which molecule has a greater attractive force? If I figure out the mass of each of them, they're essentially the same. But if I look at this molecule, it's symmetrical, and so it's not polar. If I look at this one, it's not symmetrical, so it's polar. So this would have London dispersion forces only, and this would have London dispersion and dipole-dipole forces. So it has a greater attractive force. Go ahead and draw a hydrogen bond between two ammonia molecules. This is one, so go ahead and draw another ammonia and position it so that you can form a hydrogen bond. Okay, so what we do is we draw the molecule and put in the dipoles. We then draw another molecule and we turn it so that a the dipoles are oriented correctly. Now you might have turned it so that the nitrogen was oriented over here. That's fine. It just has to be, you orient it so that a hydrogen on one molecule is adjacent to the non-bonding pair on another. And then you will draw in dotted lines. Well, here is another one, and so here, this is what you might have done, is put nitrogen over here close to a hydrogen. It doesn't, there's a lot of possibilities. There's 4 possibilities here. So if you didn't draw it exactly right, but you have the orientation right, that's good. But we're missing something. We have to draw on the hydrogen bonds. Remember that they are dotted lines, not solid lines. Solid lines are covalent bonds. Dotted lines are hydrogen bonds. Notice the del positive on a hydrogen is being attracted to the del negative and non-bonding pair on a nitrogen. The del positive on a hydrogen is being attracted to the del negative and non-bonding pair on a nitrogen. Which one of these molecules has the strongest attractive force? Well, although this has more mass than this, it's marginally so. This has a mass of 34 grams per mole, and this has a mass of 16 grams per mole, 18 grams per mole. So if I look at that's a moderate difference in London dispersion forces. This is slightly higher. But water is polar, and water has a hydrogen on the oxygen, so it can hydrogen bond. So this has the strongest attractive force. Which one of these compounds has the ability to hydrogen bond? Okay, notice this says the nitrogen is not attached to that hydrogen. You should already understand that, but I'm just emphasizing that because what you have to do to look for hydrogen bonding is find a hydrogen that is on a nitrogen or an oxygen. This nitrogen has a hydrogen on it over here. This nitrogen does not. Now this is a polar molecule and this is a polar molecule, but only this one can hydrogen bond. Which one has the greater intermolecular attractive force? Well, it's the one that can hydrogen bond. Which of the following molecules has the greatest attractive force? Well, first let's identify what are the various attractive forces. London dispersion forces here. We can have London dispersion forces, dipole-dipole, and hydrogen bonding here. And this one has London dispersion and dipole-dipole. How is it I was able to get this very quickly? Okay, with organic molecules, you look for oxygen and nitrogen. If oxygen or nitrogen are present, then it's polar and it will have dipole-dipole forces. Then I look for a hydrogen attached to the oxygen or nitrogen. This one has a hydrogen attached to the oxygen, so it's able to do hydrogen bonding. Now that I'm able to list all these intermolecular attractive forces, I can say this one has the strongest, this one has the strongest intermolecular attractive force. This one has the smallest one. Ionic compounds have attractive forces, but they're not called intermolecular attractive forces because they're not molecules. There are attractive forces between ions all over the place. That's what holds crystal lattices together for ionic compounds. Outside of crystal lattices, though, you can still have ionic attractive forces. Down here, if we look at this drawing, this right here is called a carboxylate group, and you see it on proteins. This is an ammonium group, and we see that on proteins. You see they have a negative anion, positive cation. And those opposite charges have a strong attractive force for each other. And so anytime we have opposite charges, cations and anions, they can form a strong attractive force. In this is an ionic bond. In a protein, you actually can have two groups like this attract to each other and pull the protein together at that point. And when it does that, we call it a salt bridge. Ionic compounds are made of ions, and so you're not going to see the intermolecular attractive forces that we talked about earlier. But they can be attracted to polar molecules. So here's sodium chloride, an ionic compound. When put in water, the sodium will be attracted to the del negative on the oxygen, and the negative chloride will be attracted to the hydrogen with its del positive. So this is an important interaction that allows ionic things to dissolve in polar compounds. It's called an ion dipole attraction, and this is what controls the dissolving of salt and other ionic compounds in water. What do you see? The cation is always attracted to the del negative of the oxygen, and the anion is always attracted to the del positive of hydrogen. And we're going to look at this a little bit more later on when we're looking at solutions. Now, if you're looking at intermolecular attractive forces and you want to rate them, you always look to see, you answer these questions. Is a compound polar? Well, no, then it's London dispersion forces only, and it's relative or proportional to the molar mass. If it is polar, look to see if it can have hydrogen bonding. If not, then all it has is London dispersion forces and dipole-dipole. If hydrogen bonding is possible, well, then you've got really strong attractive forces. If it turns, you look and see, is it ionic? If not, then all you have are London dispersion, dipole-dipole, and hydrogen bonding. If you've got ionic things, then it's either going to be an ionic crystal or you can have an ion dipole interaction.